stop. Before you close your eyes tonight, I need you to hear this. 3 weeks ago, scientists went through 30-year-old data from a dead spacecraft. A spacecraft that burned up in 1994. Data that had been sitting in an archive untouched, unexamined, forgotten for 3 decades. And in that data, they found something that no human being had ever seen before. A room not on Earth, not on the Moon, on Venus. A room so large that if you placed the Eiffel Tower inside it, the entire Eiffel Tower, from base to antenna, the tip would not reach the ceiling. A room with walls of solid volcanic rock. A ceiling 150 meters thick. A floor that has not been touched by light, by heat from above, by anything from the outside world in millions of years. And nobody knew it was there. It had been there the entire time, beneath one of the most hostile surfaces in the solar system. Beneath a planet where the air is hot enough to melt metal, where the pressure would flatten your body before you had time to exhale, where the sky itself is made of acid. And tonight, right now, as you let the world outside go quiet, we are going to go there. All the way down, into the tunnel beneath Venus, into a darkness that makes the darkness of space look almost comfortable, into a question that scientists are only just beginning to ask, and that may turn out to be the most important question in the history of our species. Is there something in there? Has there ever been? Welcome to Science for Sleep, the place where the universe slows down. If you are here for the first time, I am glad you found this. Stay as long as you like. And if Science for Sleep has become part of your nights, if these journeys have kept you company in the quiet hours, a like on this video and a subscription costs you nothing and means everything, it tells the universe that slow, careful, science-rooted storytelling still has a place here. The subscribe button is just below this video. It will take you 2 seconds. And then we can go. Tonight's journey begins with a planet your ancestors called a goddess. A planet scientists have called Earth's twin for over a century. A planet that in all of recorded human history has never once shown its face. Its name is Venus. And 3 weeks ago, for the first time ever, we saw something beneath its surface. Let us go. Let us begin where all good journeys begin. At the beginning, Venus is the second planet from the Sun. It orbits slightly closer to our star than Earth does, completing one full revolution every 225 days, while Earth takes 365. Its orbit brings it, at its closest approach, to within 40 million kilometers of us. In astronomical terms, that is, next door. In almost every measurable physical way, Venus and Earth are nearly identical. The two planets formed from the same cloud of gas and dust in the same region of the early solar system at approximately the same time, roughly 4.5 billion years ago. Their sizes are almost the same. Venus has a diameter just 5% smaller than Earth's. Their masses are similar. Their densities are similar. Even the strength of gravity on their surfaces is similar. If you weighed 70 kilograms on Earth, you would weigh 63 kilograms on Venus. For decades, scientists referred to Venus as Earth's twin, Earth's sister planet, the world most like our own. And then, in the 20th century, we actually went there and discovered that the twin had become a monster. The first clue was the temperature. When early calculations were made about what Venus's surface temperature might be, scientists initially hoped it might be warm but tolerable, perhaps something like a tropical Earth, perhaps warm enough for liquid water, perhaps even hospitable to some form of life. The reality was something different. 465 degrees Celsius. Not 465 degrees at the equator in summer. Not 465 degrees in the direct sunlight. 465 degrees everywhere, at all times, on the surface, in the shadows, at the poles, in the valleys, on the mountaintops, day and night, with no variation, no season, no reprieve. This is hot enough to melt lead, hot enough to melt tin, zinc, and bismuth. Hot enough that any spacecraft we have ever sent to the Venusian surface has been destroyed within hours of landing, not by any mechanical failure, but simply by the ambient heat of the air around it. The second clue was the pressure. At sea level on Earth, the atmosphere exerts a pressure of 1 atmosphere, the weight of all the air above your head, which you do not feel because every creature on this planet has evolved to live comfortably within it. On the surface of Venus, the atmospheric pressure is 93 atmospheres, 93 times the pressure you feel right now as you breathe. This is equivalent to the pressure you would experience if you descended almost a kilometer beneath the surface of Earth's oceans. At that depth, every square inch of your body would be subjected to a weight that would crush it completely. Standing on the surface of Venus, without protection, would not feel like standing on another planet. It would feel like being at the bottom of the sea, inside an oven, on the hottest day you can imagine, multiplied by a factor that your body was never designed to survive. The third clue was the clouds, those beautiful, brilliant white clouds that make Venus so visible from Earth. Those are not water clouds. They are made of sulfuric acid, concentrated sulfuric acid, in droplets fine enough to create a permanent haze that wraps the entire planet and never breaks. In the cloud layer itself, the wind speeds reach 360 kilometers per hour. Hurricanes, sustained and permanent, circling the entire planet continuously. Between the cloud layer and the surface, the atmosphere is mostly carbon dioxide, nearly 97% of it, thick enough that almost no light reaches the ground. What does reach the surface is reddish and dim, scattered and diffused by the layers above. On Venus, there are no sunrises, no blue sky, no stars visible at night, no seasons, no weather as we understand it, only the permanent, uniform, crushing heat, and above it, the acid clouds moving endlessly in their planetary scale hurricane. This is Venus, the planet so like Earth in every measurable physical property, and so catastrophically different in every lived reality. How did it get this way? The answer begins with the planet's extraordinary relationship with heat. Venus is slightly closer to the Sun than Earth. That alone would make it warmer, but not catastrophically so. The additional solar energy Venus receives compared to Earth is not enough, on its own, to produce temperatures of 465 degrees. What produces those temperatures is what happened to Venus's atmosphere. At some point in Venus's history, perhaps triggered by intense volcanic activity, perhaps by a slight increase in solar energy, as the sun slowly brightened over billions of years, the planet entered a runaway greenhouse effect. Carbon dioxide, released by volcanoes, accumulated in the atmosphere. Carbon dioxide traps heat. As the atmosphere warmed, it became capable of holding more water vapor, and water vapor traps even more heat. The ocean, if it existed, began to evaporate. More water vapor entered the atmosphere. More heat was trapped. The temperature rose further. More evaporation. More heat. A loop with no exit. A feedback cycle that, once begun, could not be stopped. The result is the Venus we see today. A world where the greenhouse effect has gone so far beyond anything Earth has ever experienced that the surface temperature is higher than the surface of some stars. But here is what makes this story important, and what brings us to the discovery made in February of 2026. This process, the transition from a potentially habitable world to the hellscape Venus has become, was not instantaneous. It took hundreds of millions of years. And during those hundreds of millions of years, if life had ever managed to begin on Venus, if the chemistry had ever organized itself into something that could grow and reproduce and adapt, that life would have had time to respond, to move, to find refuge. And the discovery made at Nyx Mons in 2026 suggests that there may be exactly the kind of refuge such life would have needed, hidden beneath the surface, protected by 150 meters of solid volcanic rock, in the dark. We have been trying to understand Venus for a very long time. The first spacecraft to successfully fly past another planet was Mariner 2 in 1962. Its destination was Venus. The data it sent back confirmed that Venus's surface was extraordinarily hot the first time any instrument had ever measured conditions on another world. Since then, we have sent 43 missions to Venus. The Soviet Union sent the most as part of their Venera program, a series of probes that, over decades of engineering and experimentation, eventually managed to land on the Venusian surface, survive long enough to take readings, and in some cases send back photographs. The images those cameras captured are among the most otherworldly in the history of space exploration. A flat, orange-tinted landscape, slabs of dark rock, angular and strange. The sky above a thick, featureless orange-brown haze. No movement, no variation, nothing that looks like home. The Soviet landers that captured these images survived for between 23 minutes and 2 hours before being destroyed by the heat and pressure. They were over-engineered for every conceivable condition built to withstand what was expected to be a harsh environment, and still Venus killed them faster than their designers had planned. NASA's approach to Venus was different. Rather than landing, NASA sent spacecraft to orbit, to map, to listen. The Pioneer Venus mission, launched in 1978, used radar to make the first rough maps of the Venusian surface from orbit. It revealed, for the first time, that Venus had mountains, valleys, and what appeared to be volcanic features. But the most comprehensive mapping mission, the one that produced the data still being analyzed to this day, was Magellan. Magellan launched in May of 1989 and arrived at Venus in August of 1990. For the next 4 years, it orbited the planet continuously, firing radar pulses through the clouds and listening to the echoes that returned. The technique is called synthetic aperture radar, or SAR. It works because radio waves, unlike visible light, can pass through clouds. They travel through the thick Venusian atmosphere, bounce off the solid surface below, and return to the spacecraft, carrying in their echo the shape and texture of whatever they struck. By analyzing these echoes carefully, Magellan constructed a radar map of nearly the entire surface of Venus, the most detailed global map of any planet other than Earth that existed at the time. What that map revealed was astonishing. Volcanoes. Hundreds of thousands of them. From small shields a few kilometers across to massive structures hundreds of kilometers in diameter, rising several kilometers above the surrounding plains. Scientists estimate that Venus may have close to 1 million volcanic features on its surface, more than any other planet in the solar system. Lava plains stretching for thousands of kilometers. Vast, flat expanses of solidified volcanic rock covering most of the planet's surface in layer after layer of ancient eruptions. Channels. Long, sinuous channels carved into the surface by flows of lava so hot and so fluid that they behaved almost like rivers, meandering, branching, cutting their way across the landscape over hundreds of kilometers. One of these channels, named Baltis Vallis, is the longest known channel in the solar system, running for nearly 7,000 kilometers. Longer than the Nile River, longer than any river on Earth. Not carved by water, carved by fire. And scattered across this volcanic landscape, Magellan also recorded something else, something that planetary scientists noticed, but did not, at the time, have the tools to fully investigate. Pit chains. Long lines of circular depressions, following straight paths across the surface for hundreds of kilometers. Places where the ground had collapsed, leaving a series of holes like a series of sinkholes, but in volcanic rock, following a perfectly linear path. Scientists had a theory about these pit chains. The theory was this: beneath the surface, following the same path as the pit chain above, there was a hollow tube, a tunnel carved by ancient lava, a lava tube with the pit chain on the surface marking the places where the tunnel's ceiling had partially collapsed. It was a reasonable theory. It was consistent with everything known about volcanic geology, but it was only a theory, because Magellan's radar could not see beneath the surface. Confirming the theory would require something different. A new technique, a new analysis, a new way of looking at old data. It would require someone willing to ask, 30 years after Magellan fell silent, whether there was something in its echoes that no one had yet heard. Professor Lorenzo Brusone was willing to ask. Lorenzo Brusone is a professor of telecommunications at the University of Trento in Italy. His specialty is remote sensing, the science of gathering information about distant objects without physically touching them. His laboratory has spent years developing techniques for analyzing radar data, specifically for finding things beneath the surface of planets using the echoes of radar signals. This is not a simple problem. When a radar signal travels from a spacecraft, bounces off a planet's surface, and returns, the echo contains information about what it struck, the strength of the return signal, the angle at which it reflected, the time it took to arrive back, the texture of the surface it hit. But a standard radar system looking at a standard planetary surface cannot see underground. The signal hits the surface and bounces back. The underground environment is invisible, unless there is an opening. This is the key insight behind the University of Trento's technique. Near a skylight, near one of those circular pits where the ground has collapsed, the radar signal behaves differently. When the signal hits the pit, some of it enters the underground void below. It travels down into the tunnel, bounces off the walls and floor of the cavity, and returns to the surface carrying information about the underground space. The challenge is distinguishing this second, weaker, more complex return signal from all the noise of the surrounding radar data. It requires specialized processing, detailed analysis, software algorithms trained specifically to recognize the signature of an underground void in radar imagery. This is exactly what Bruzone and his colleagues had developed and refined over years of work. And in 2024, they decided to apply it to Magellan's data. Specifically, they focused their analysis on the region of Nyx Mons, a massive shield volcano on Venus's western hemisphere, surrounded by extensive pit chain systems that had long been considered the most promising candidate location for subsurface lava tubes. Nyx Mons itself is enormous, a shield volcano 362 kilometers in diameter, larger than many countries. It rises from an already elevated volcanic plateau, its broad, gentle slopes the product of countless eruptions layered over millions of years. On its western flank, Magellan's radar had recorded a series of pit chains stretching across the terrain, and within those pit chains, one feature in particular caught the team's attention: a single pit, slightly larger than the others in its chain, showing radar backscattering characteristics that were subtly but distinctly different from the surrounding pits. The team labeled it simply as Pit A, and when they applied their specialized imaging technique to Pit A, the data told them something unmistakable. Beneath it, there was something hollow. The radar signal entering Pit A was returning with a pattern characteristic of an underground void, a large, open, empty space beneath the surface. The team processed and reprocessed the data, applying their technique from multiple angles, checking their results against the known characteristics of false positives and measurement errors. The signature remained consistent, clear, reproducible. There was something there. The next step was to characterize it, to determine, as precisely as the available data allowed, how large the underground void was. The results, when they emerged, were larger than anyone had expected. The conduit, the underground tunnel, had an estimated diameter of approximately 1 kilometer, not the width of a narrow cave or a mine shaft. 1 kilometer. The width of 10 football fields, placed end to end. The roof of the tunnel, the rock ceiling separating the hollow space below from the surface above, was at least 150 meters thick. 150 meters of solid volcanic basalt, unbroken, forming a natural arch over the empty space below. And the height of the empty void from the floor of the tunnel to the underside of that rock ceiling was no less than 375 meters. 375 meters. Pause for a moment and let that register. The Eiffel Tower, from its base to the tip of its antenna, stands 330 meters tall. The tunnel beneath the surface of Venus, the empty space inside, from floor to ceiling, is taller than the Eiffel Tower. The Empire State Building, from its lobby to the roof, stands 443 meters. You could fit the Empire State Building inside this tunnel and still have room above it. And this is the dimension confirmed from Magellan's limited radar data, a single vantage point, 30-year-old technology that the researchers knew had significant limitations. The actual tunnel is very likely larger than what the data can confirm. In terms of its length, how far the tunnel extends beneath the surface, the researchers estimate that the subsurface conduit system may extend for at least 45 kilometers through the rock of Nyx Mons' western flank. 45 kilometers. The length of a city from one end to the other. Beneath the surface of Venus, empty, hollow, dark, and waiting. The discovery was published in Nature Communications on February 9, 2026. Our knowledge of Venus is still limited, Bruzone said, and until now we have never had the opportunity to directly observe processes occurring beneath the surface of Earth's twin planet. The identification of a volcanic cavity is therefore of particular importance. 30 years of data. Sitting in an archive, waiting for someone to look more carefully, let us pause for a moment and consider what we are actually talking about. Because the words lava tube can sound almost ordinary, clinical, like something in a geology textbook that you might read once and forget. They are not ordinary. A lava tube is one of the most dramatic natural structures in planetary geology, and understanding what they are and how they form is essential to understanding why this discovery on Venus matters so profoundly. When a volcano erupts, the lava that flows from it does not all behave the same way. At the surface, where lava is exposed to the cooler air, it begins to harden quickly. A crust forms, a shell of solid rock over still molten rock beneath. But underneath that crust, the lava continues to move. It flows onward, away from the volcano, channeled by the solid walls that have formed around it, like a river inside a pipe, like water moving through a hose. And then, when the eruption ends, when the supply of lava from the volcano stops, the liquid inside drains away, flows onward, disappears into the lower ground, or simply cools and contracts. What remains is the pipe, a hollow tube of rock, solid roof, solid walls, solid floor, empty inside. This is a lava tube. On Earth, we know them well. The Hawaiian Islands are threaded with lava tubes, some stretching for dozens of kilometers beneath the volcanic landscape. You can walk inside them, explore them, stand in chambers large enough to contain entire buildings. The largest known lava tube on Earth, Kazumura Cave in Hawaii, extends for over 65 kilometers underground. But even Kazumura Cave, extraordinary as it is, would fit inside the Venus tube discovered at Nyx Mons. The dimensions are simply different at that scale. Lava tubes have also been found on the Moon and on Mars. The discovery of each one raised the same set of questions that planetary scientists are now asking about Venus. What is inside them? How stable are they? And could anything live there? On the Moon, scientists have proposed that lava tubes could serve as natural shelters for future human settlements. The thick rock ceiling would block harmful solar radiation. The stable underground temperature constant, unlike the extreme heat and cold of the lunar surface, would make the environment far more manageable for any structure or life system placed inside. Engineers studying lunar lava tubes have calculated that a tube large enough could potentially shelter an entire city, that the rock overhead could provide radiation protection equivalent to a thick concrete bunker, that inside the tube, temperatures would remain stable while the surface above swung between positive 120 degrees in sunlight and negative 170 in darkness. On Mars, the same logic applies and has been extended further. If microbial life ever existed on Mars, the underground environment of a lava tube protected from the intense ultraviolet radiation that now sterilizes the Martian surface, potentially retaining liquid water at depth, sheltered from the cold by the insulating rock above, would be among the most favorable places for it to survive long after the surface became hostile. Scientists studying Mars have seriously proposed that if we want to find life on that planet, we should not be drilling into the exposed surface. We should be looking in the tubes. And now, Venus, where the surface temperature is 465 degrees Celsius, where the atmospheric pressure would crush a human body instantly, where the sky rains sulfuric acid. But underground, beneath 150 meters of solid rock, something is different. The temperature at depth is not the same as the temperature at the surface. Rock is an insulator. The deeper you go beneath the surface, the more stable the temperature becomes, buffered from the extreme conditions above by the sheer mass of material between the underground space and the sky. Scientists do not yet know exactly what temperature exists inside the Nyx Mons lava tube. The data does not exist, but they can model it, and what those models suggest is significant. The surface temperature of Venus is 465 degrees. The interior of Venus is considerably hotter still, but at the depth of 150 meters, at the floor of a tube that stretches kilometers beneath the surface, the temperature might be something in between, something lower than the surface, something that, in the context of what we know about extremophile life on Earth, might not be impossible. Might not be impossible. That is not a claim. It is not a prediction. It is a door that the discovery at Nyx Mons has opened, where before there was only a wall. Here is something remarkable about the Venus lava tube that the University of Trento team confirmed. It is bigger than any lava tube found on Earth, and the reason why tells us something profound about how planetary environments shape the geology that forms within them. On Earth, the formation of a lava tube depends on several factors: the viscosity of the lava, the speed of the flow, the slope of the terrain, and the temperature of the surrounding environment. On Venus, two specific conditions appear to favor the formation of unusually large, unusually stable lava tubes. The first is gravity. Venus's surface gravity is slightly lower than Earth's, about 90% as strong. This might seem like a small difference. In practice, for the process of lava tube formation, it matters considerably. When lava flows across a surface, the behavior of the molten rock, how it moves, how quickly it cools, how the outer crust forms, is influenced by gravity. Lower gravity means that the lava flows slightly differently. The outer crust that forms as the lava is exposed to the surrounding environment develops more slowly and more thickly than it would under Earth's stronger gravitational pull. A thicker crust means a stronger roof. A stronger roof means a larger void can form beneath it without collapsing. And a larger void means a larger lava tube. The second factor is the atmosphere. Venus's dense, hot atmosphere surrounds the surface at all times. While this makes the surface itself brutally hostile, it also means that the temperature differential between the flowing lava and the surrounding environment is considerably smaller than it would be on Earth or the Moon. On Earth, the contrast between molten lava and the cool open air is dramatic. This dramatic contrast drives rapid cooling, and rapid cooling means that lava tube roofs form quickly, which limits their thickness and structural strength. On Venus, the surrounding atmosphere is itself extremely hot. The contrast is smaller. The cooling is slower and more gradual. This allows the lava tube structure to develop over a longer period, creating a more robust and more enduring underground channel. The combined effect of lower gravity and a hotter surrounding environment produces lava tubes on Venus that are, by the analysis of the Trento researchers, structurally superior to those on Earth. Wider, more stable, more likely to survive intact over geological timescales. And because Venus is covered in nearly 1 million volcanoes, more than any other planet in the solar system, the planet's history of intense volcanic activity may have produced not just one such tube, but an entire network of them. The University of Trento team did not analyze only Pit A and Nyx Mons. They also examined several other pit chain systems across Venus's surface using the same technique. Their results, reported in the same Nature Communications paper, suggest that subsurface conduit signatures are present at multiple locations across the planet. Multiple potential lava tube systems, stretching, potentially interconnected, beneath the scorched and hostile surface. A hidden world beneath a hidden world. A network of tunnels in the dark. And here is where the question becomes not just geological, but existential. If Venus once had the conditions for life, and the evidence suggests it might have, and if those conditions changed gradually over hundreds of millions of years, and the evidence suggests they did, and if underground lava tubes on Venus are larger, more stable, and more thermally buffered than anything we have on Earth, and the evidence now suggests they are, then where, exactly, would life have gone? This is not a fringe question. It is one that serious planetary scientists have been asking for decades, and the discovery at Nyx Mons has given it a new and urgent relevance. Because Venus was not always the hellish world it is today. Current models of planetary formation and evolution built from decades of spacecraft data, computer simulations, and comparative planetology suggest that billions of years ago, Venus may have been a very different place. A planet with a thinner atmosphere. A planet with lower surface temperatures. A planet that, the models suggest, may have had liquid water on its surface for a period of time. How long? The estimates vary. Some researchers have modeled scenarios in which Venus maintained habitable surface conditions for as little as a few 100 million years. Others have proposed that the window may have extended for as long as 2 to 3 billion years, meaning Venus may have been habitable for roughly the same amount of time that life was developing and evolving on Earth. 2 to 3 billion years. On Earth, the first microbial life appeared approximately 3.5 billion years ago. In the 3 billion years since, life has gone from simple single-celled organisms to the extraordinary diversity of species that covers every surface of this planet today. If Venus had 2 to 3 billion years with liquid water and a reasonably stable climate, the same chemistry that produced life on Earth had plenty of time to operate on Venus as well. And then something changed. The runaway greenhouse effect triggered by increasing solar luminosity, by a period of catastrophic volcanic activity, or by some combination of factors still debated by scientists, transformed Venus from a potentially habitable world into what it is today. The oceans, if they existed, evaporated. The water vapor entered the atmosphere and over millions of years was broken apart by solar radiation and lost to space. The surface temperature climbed, the pressure rose, the clouds of sulfuric acid formed, and any life that had developed on Venus faced a choice that was no choice at all: adapt or disappear. Some scientists have proposed that life on Venus, if it ever existed, may have adapted to survive in the cloud layer in the temperate zone of Venus's upper atmosphere, where temperatures and pressures are actually somewhat Earth-like, where liquid water droplets may still form, where sunlight is available. This hypothesis was given unexpected support in 2020 when a team of astronomers reported the detection of phosphine in Venus's cloud layer. Phosphine, a molecule that, on Earth, is produced primarily by microbial life, had no convincing abiotic explanation for its presence. The discovery was controversial. It remains contested. The data have been reanalyzed multiple times, with different researchers reaching different conclusions about whether the signal is real and what, if anything, it means. But the controversy itself is significant. It means the question of life on Venus is taken seriously. Seriously enough for major scientific teams to examine the data with extraordinary care. Seriously enough for space agencies to plan missions specifically designed to investigate it. And now, with the confirmation of a lava tube beneath the surface, there is a second possible refuge to consider. Not the clouds, the ground. Deep underground, in the dark, protected by 150 meters of rock from the heat and pressure above, in a space large enough to contain an entire city, in a tunnel that may extend for dozens of kilometers through the most volcanically active terrain on the planet. The University of Trento researchers were measured in their language, as scientists must be. They did not claim to have found life. They did not even speculate openly about it in their paper. But they were explicit about one thing. The lava tube at Nyx Mons, they wrote, represents a potential site for astrobiology investigations. It may preserve stable thermal conditions. It provides shielding from the extreme surface temperature. It may harbor conditions significantly different from the uninhabitable environment above. This is the language of possibility. The door, once a wall, is now open. The discovery of the Venus lava tube is not just a scientific result. It is a destination. 2 major missions to Venus are currently in development, and both have been directly energized by what the University of Trento team found in Magellan's old radar data. The first is NASA's Veritas mission, Venus Emissivity, Radio Science, INSAR, Topography, and Spectroscopy. Veritas is designed to map Venus's surface at significantly higher resolution than Magellan ever achieved. Where Magellan could see features roughly the size of a football field, Veritas will be able to see features the size of a small building. The difference matters enormously for lava tube detection. The small skylights, the surface pits that indicate a lava tube beneath, will be far easier to identify and characterize at Veritas resolution. What the University of Trento team found, by carefully analysing Magellan's limited data, Veritas may find dozens or hundreds of times over. The entire surface of Venus, mapped at a resolution that makes individual volcanic features visible. Every pit chain, every skylight, every potential entrance to a network of underground tunnels that may extend for thousands of kilometers beneath the surface. The second mission is the European Space Agency's Envision. Where Veritas focuses on surface mapping, Envision carries something even more directly relevant to lava tube investigation. An orbital ground-penetrating radar. A radar system capable of probing several hundred meters beneath Venus's surface, not just seeing the surface, but seeing through it, imaging what lies below. If the lava tube at Nyx Mons is real, and the University of Trento researchers are confident it is, Envision will confirm it directly. Not from echoes bouncing off a skylight entrance, but from direct radar imaging of the underground conduit itself, its roof, its walls, its floor, its extent, and it may find others, many others. Both missions are expected to launch before 2031. In the history of planetary science, that is not very far away. The hidden world beneath Venus may not remain hidden for much longer. Let us take a step back from the science for a moment and think about what this discovery actually tells us. Not about Venus, about us. NASA's Magellan spacecraft last communicated with Earth in October 1994. It has been silent for over 30 years. The engineers who built it have mostly retired. Some have died. The technology it used to gather its data was state-of-the-art in 1989, which means it is now, by the standards of modern computing and signal processing, almost antique, and yet the data it collected, archived, stored, preserved in the databases of the Jet Propulsion Laboratory, just told us something about our nearest planetary neighbour that no one in the history of science had ever known before. There is a tunnel beneath Venus, a vast, ancient, hollow tunnel formed by fires that burned millions of years before the first human walked on Earth. We did not need a new spacecraft to find it. We needed someone willing to look more carefully at what we already had. Lorenzo Brusone and his team at the University of Trento asked the right question, and 30-year-old radar echoes answered. This pattern, old data yielding new discoveries when approached with new tools and new questions, runs through the history of science like a thread. The discovery is not always in the new data. Sometimes it is in the old data, waiting patiently for the right moment, for the right technique, for the right mind to sit down, look carefully at an archive of radio echoes from a dead spacecraft, and think, what are we missing? What else is in here that no one has seen yet? Magellan answered that question with a tunnel named after the goddess of the night, hidden beneath a volcano named after the goddess of the night, on a planet that has spent all of recorded human history keeping its secrets. Venus has always been a world of mysteries. This is simply the latest one we have been allowed to uncover. Right now, as you settle into wherever you are listening to this, Venus is somewhere in the sky above you. You may not be able to see it. The clouds, the daylight, the walls of the room you are in, any of these may stand between you and it, but it is there, as it always is, tracing its orbit around the Sun, completing its ancient, unbroken circuit, the same circuit it has been making for 4.5 billion years. And beneath its surface, beneath the acid clouds and the crushing atmosphere and the lava plains that stretch for thousands of kilometers, there is a tunnel, empty, ancient, taller than the Eiffel Tower, wide as a city block, stretching for kilometers through rock that has not felt movement or light since before the first human civilization, before the first human language, before the first human thought. We found it by asking a question no one had asked in quite that way before, by applying a technique developed for other purposes to data gathered by a spacecraft that has been silent for 30 years, by refusing to assume that everything interesting in an archive had already been found. And what we found has changed what we know about Venus. Not dramatically, not with the thunder of a paradigm-shattering discovery announced on the front page of every newspaper, quietly. The way the best discoveries often come. A paper in a journal, a press release, a few articles in the science press, and then the slow, spreading realization that the solar system is, once again, larger and stranger and more full of possibility than it was the day before. Venus has a tunnel, and that tunnel might have sheltered life once, and might, against all odds, against the most hostile surface conditions in the solar system, shelter something still. We do not know. We will not know until we go back. But we know, now, that there is somewhere to look. That is not a small thing. In the history of the search for life beyond Earth, a search that has been ongoing in one form or another, for as long as humans have looked up at the sky, the identification of a new candidate location is not a small thing at all. It is everything. Sleep well. Somewhere in the darkness above you, a planet is keeping its secrets. But fewer of them now than yesterday, and fewer still tomorrow. We have talked about Venus from a distance, from orbit, from radar echoes, from mathematical models and the careful, detached language of scientific papers. But there is another way to understand a place. You go there, or you send something that goes for you. Between 1970 and 1984, the Soviet Union sent a series of spacecraft to the surface of Venus. They were called the Venera probes, named after the Russian word for Venus itself. And the story of those missions is one of the most extraordinary chapters in the history of space exploration. Not because they were triumphant, not because they returned heroes safely to Earth, but because they tried, again and again, against a planet that seemed determined to destroy everything we sent it. The Soviet engineers tried. The first attempts failed completely. Venera 1 lost contact with Earth before it even reached Venus. Venera 3, in 1966, became the first spacecraft from Earth to reach the surface of another planet, but it was not designed to survive the impact, and it carried no instruments capable of transmitting from the surface. It crashed. It was silent. There was nothing to hear. The engineers went back to their drawing boards. They had assumed, based on the best available data, that Venus's surface conditions might be survivable with the right engineering. They were wrong. The first probes to attempt a soft landing were destroyed by the pressure and heat before they reached the ground, so they built stronger ones. Spherical capsules, reinforced with titanium, pressurized to withstand the crushing atmosphere, insulated with layers of material designed to keep the internal electronics cool long enough to function, equipped with parachutes to slow the descent through the upper atmosphere, and then, when it became clear that parachutes were unnecessary in the thick lower atmosphere, redesigned to use the air resistance of the dense Venusian air itself as a brake. The engineering was extraordinary. The challenges were unlike anything ever attempted. Think about what they were trying to do. They were building a machine that had to survive being dropped through an atmosphere of sulfuric acid clouds moving at 360 kilometers per hour, then slow itself in an atmosphere 93 times denser than Earth's, then land without shattering on a surface that was 465 degrees, then operate taking readings, sending data in conditions that would melt most metals within hours, and then do it again, and again, and again. On December 15th, 1970, Venera 7 became the first spacecraft in history to successfully land on another planet and transmit data from the surface. It survived for 23 minutes. 23 minutes in 465-degree heat, under 93 atmospheres of pressure, on a surface that no human being would ever stand on. In those 23 minutes, it measured the temperature. It measured the pressure. It confirmed, definitively, and for the first time, that the surface of Venus was exactly as hostile as the worst estimates had predicted. The scientists who received those 23 minutes of data wept, not from disappointment, from relief, from the extraordinary, almost unbearable emotion of having sent a machine to another world and having it call back. It called back for 23 minutes, and then the heat took it. The missions continued. Each one survived a little longer. Each one sent back a little more data. And then, in 1975, Venera 9 did something that had never been done before in the history of space exploration. It took a photograph, not an artist's impression, not a diagram, not a computer reconstruction, a photograph of the surface of another planet. The image that came back showed a landscape of angular, sharp-edged rocks, surprisingly fresh-looking, not worn smooth by erosion the way Earth's rocks are. The light was dim and reddish, filtered through the thick atmosphere above. The horizon was not visible. The ground was close and immediate, and utterly, completely alien. Scientists stared at it for a long time. This was Venus, the planet that had been a bright white point of light in the sky since before history. The planet of love and beauty and mystery. The planet your ancestors named after a goddess. This was what it actually looked like. Rocks, orange light, a crushing, invisible weight pressing down on everything. Subsequent Venera missions sent back more photographs. The images were all variations on the same theme: rocky, orange, flat, lifeless in every visible sense. The sky above the cameras was a uniform orange-brown haze that faded into nothing a few hundred meters away. The last Soviet landers on Venus Venera, 13 and 14 inches, 1,982, survived for over 2 hours. They transmitted color images. They analyzed soil samples. They measured seismic activity. They listened to the sounds of Venus. And yes, Venus has sounds. Low, rumbling sounds. The sound of an atmosphere so dense and so pressurized that even the faint movements of air near the surface are enough to register as a kind of deep, continuous murmur. The scientists who analyzed the sound recordings describe them as something between the sound of a very deep ocean and the sound of a room full of machinery running at low power. A sound like something alive. Though what was alive down there, if anything, remained, and remains today, the great unanswered question. The Venera program ended in 1984. No spacecraft has landed on Venus since. The surface has been silent again. For over 40 years, waiting, there is another reason this discovery matters. A reason that has nothing to do with tunnels or lava tubes or the possibility of ancient life. A reason that is much closer to home. Venus is a warning. When scientists study the runaway greenhouse effect that transformed Venus from a potentially habitable world into the most hostile surface in the solar system, they are not simply doing planetary science for its own sake. They are studying a process that could, under the right conditions, happen here. Not in our lifetimes. Not in 1,000 years. Probably not in 100,000 years. But the physics is the same. The same carbon dioxide that is accumulating in Earth's atmosphere right now from the burning of fossil fuels, from deforestation, from industrial processes, is the same carbon dioxide that triggered the runaway greenhouse on Venus. The difference is one of degree and timescale. On Venus, the process ran to completion. The feedback loops had nothing to stop them. The ocean evaporated entirely. The water was broken apart by solar radiation and lost to space atom by atom over millions of years. The carbon dioxide reached concentrations of 97% of the atmosphere. The temperature reached 465 degrees and stayed there. On Earth, the process has not run to completion. The ocean is still here. The carbon cycle, the complex web of processes by which carbon moves between the atmosphere, the oceans, the land, and living things, is still functioning, still absorbing some of what we emit, but it is absorbing less than we are putting in. The concentration of carbon dioxide in Earth's atmosphere has risen from 280 parts per million before the Industrial Revolution to over 420 parts per million today. That is an increase of 50% in roughly 200 years. In geological terms, 200 years is nothing. It is a breath. It is less than a heartbeat in the 4.5 billion year history of this planet. And in that single geological breath, we have changed the composition of the atmosphere by 50%. Venus does not judge us for this. Venus does not offer an opinion. Venus simply exists a demonstration, written in 465-degree temperatures and crushing atmospheric pressure, of what a runaway greenhouse effect looks like when it has finished its work. Scientists who study Venus are not, by and large, alarmists. They are careful, methodical people who follow data where it leads, and the data leads them, repeatedly, back to the same conclusion. Planetary climates are not stable by default. They are stable because of a specific set of conditions that balance warming against cooling, absorption against emission, evaporation against precipitation. Disturb those conditions enough, shift enough variables far enough from their equilibrium and the balance tips. Venus tipped. We do not know exactly when. We do not know exactly why. We do not know whether it was inevitable, given Venus's distance from the Sun and the composition of its interior, or whether different circumstances might have produced a different outcome. These are the questions that Veritas and Envision are specifically designed to help answer, because understanding when and how Venus became uninhabitable is not just about Venus. It is about understanding the edges of habitability itself, about learning where the lines are, and about understanding, with everything we know and everything we are still learning, how to make sure the planet we call home never crosses them. The discovery at Nyx Mons is extraordinary, but it is not unique. Lava tubes have been found or strongly suspected on several worlds in our solar system, and each one tells a slightly different version of the same story. The story of how fire shapes the insides of worlds, how lava, moving through rock the way water moves through a pipe, leaves behind hollow corridors that can persist for millions or billions of years after the fire itself has gone cold. Let us travel, for a moment, to those other tunnels. Let us see what fire has left behind across the solar system. The Moon, Earth's moon, our closest neighbour, is covered in ancient lava plains. The dark regions you see on the Moon's face when it is full, the ones that ancient astronomers called mare, meaning seas, because they thought they were bodies of water, are vast solidified lava fields, formed by eruptions that occurred between 3 and 4 billion years ago. And beneath some of those lava plains, there are tubes. In 2009, the Japanese lunar spacecraft Kaguya detected a large pit in the Marius Hills region of the Moon, a circular opening in the lunar surface approximately 65 meters across, dropping vertically into darkness below. When the Lunar Reconnaissance Orbiter photographed the pit in detail, the images showed something remarkable. The walls of the pit were undercut. The opening was smaller than the space below it. The pit was not a simple hole in the ground, it was a skylight, an entrance to a larger underground volume extending horizontally beneath the surface. Scientists estimated that the tube connected to this skylight could be hundreds of meters wide and potentially kilometers long. On the Moon, a lava tube of that size would be more than a geological curiosity. It would be a home. The lunar surface is one of the most hostile environments reachable from Earth. No atmosphere means no protection from solar radiation, the same ultraviolet and particle radiation that Earth's atmosphere quietly absorbs every single day, invisibly, continuously, without us ever noticing. Temperature swings of nearly 300 degrees between lunar day and night. Micrometeorites striking the surface constantly, with no air to slow them down. Inside a lava tube, all of that changes. The rock ceiling absorbs the radiation. The underground temperature stays constant, not warm, but stable, somewhere around -30 degrees Celsius. The micrometeorites cannot reach the interior. The chaos of the surface disappears. Engineers at NASA and ESA have seriously studied lunar lava tubes as potential sites for permanent human settlements. Not as a science fiction concept, as an engineering proposal with real calculations behind it. The calculations suggest that a lunar lava tube large enough, perhaps a kilometer across, could be sealed at its entrances and pressurized, could become, essentially, a pressurized underground city, protected from radiation by the rock above, thermally stable, shielded from the relentless hostility of the surface. Mars. The red planet is covered in ancient volcanoes, and on Mars, lava tubes have been identified in multiple regions. The largest suspected Martian lava tube, in a region near the enormous volcano Nyx Mons, may extend for hundreds of kilometers through the Martian subsurface, hundreds of kilometers, on a planet where the surface is bathed in ultraviolet radiation, where the average temperature is -60 degrees, where liquid water cannot exist in the open air. Hundreds of kilometers of underground tunnels shielded from the surface, potentially harboring the only conditions on Mars where liquid water could exist, where life could find the energy it needs, where the worst of the Martian environment simply cannot reach. Scientists studying Mars have seriously proposed, if we want to find life on that planet, we should not only be drilling into the exposed surface, we should be looking in the tubes. The tubes are where the answers might be hiding. And now Venus, where the tubes appear to be larger than on the Moon, larger than on Mars, larger than anything we have found on Earth. The solar system, it turns out, is threaded with tunnels, hollow corridors carved by ancient fire, preserved by the cold and the dark and the silence, stretching beneath the surfaces of worlds we thought we understood. The Moon, Mars, Venus, perhaps others we have not yet mapped closely enough to see. We are only beginning to count them. We are only beginning to ask what might be inside. Let us try something different for a moment. Let us set the science aside just briefly and simply be there. Imagine it. You are standing at the entrance to the Nyx Mons lava tube. At the edge of the skylight, the pit in the surface of Venus that scientists labeled Pit A in the Magellan data. The sky above you is not black, it is orange. A thick, diffuse orange-brown haze that presses down from above, carrying heat the way a blanket carries warmth. Not comfortable warmth, oppressive warmth. The kind that tells your body very clearly that it was not built for this. The light is dim and strange. Everything is illuminated, but nothing casts a sharp shadow. The sun is up there somewhere, above the cloud layers, above the acid haze, but its light has been filtered and scattered so many times by the time it reaches the surface that it arrives as a diffuse orange glow rather than a beam. There are no shadows on Venus. Not real ones. Just a uniform, sourceless light, the color of a fire dying down. The ground beneath your feet is volcanic rock. Dark, dense basalt, slightly rough under the soles of your suit. Not smooth, the way you might imagine an alien world. Textured, real, and before you is the pit. It drops away vertically, the walls perfectly sheer, carved clean by the collapse of ancient rock above whatever lay below. You cannot see the bottom from the edge. The darkness inside the pit is complete. It is a different kind of darkness than the dim orange light of the surface. It is the darkness of a place that has not seen any light, of any kind, in millions of years. You think, I am looking at a darkness older than our species. You begin to descend. The walls of the pit pass you on both sides. Smooth, basalt, dark, grey, unmarked. The orange sky above shrinks as you go down a circle, then an ellipse, then a small bright smear against the dark rock, then gone. And then you clear the bottom of the entrance shaft and the tunnel opens around you. It is vast. This is the word that comes first and stays. Vast. Not the vastness of space, which is a vastness you understand intellectually but cannot feel in your body. This is a physical vastness, a space so large that your light does not reach the far wall. The ceiling above you is lost in shadow, even knowing it is there, even knowing it is 150 meters of solid rock between you and the surface of Venus. You cannot see it clearly. It simply fades into black above your head. The floor beneath you is flat and even cooled lava, smooth where the last flow froze in place millions of years ago. There are no footprints here, no tracks of any kind, no sign that anything has ever moved across this surface. You are the first, or perhaps not the first. That is the question you cannot stop thinking about. The silence is different from the silence of the surface. On the surface, the thick atmosphere carries faint sounds, the deep murmur of pressure differentials of the planet's own geological breathing. Here, below the surface, that sound is gone. This is a deeper silence, the silence of a place that has been sealed from the universe for an unimaginable span of time. You walk forward. The tunnel extends ahead of you in both directions, curving gently away from sight, following the ancient path of the lava that carved it. The walls are not perfectly smooth. They are layered, showing the history of the flows that passed through here, each eruption leaving its mark in the rock. A geological diary written in basalt. The temperature, your instruments tell you, is lower here than at the surface. Not comfortable, not safe without the suit, but lower, measurably, meaningfully lower. The rock above is doing exactly what physics said it would do, insulating, buffering, creating, in this enclosed underground space, a microenvironment that is different from the world above. How different? That is what we do not know yet. That is why the missions are coming. You stop. You turn off your light. The darkness is complete and perfect. You cannot see your hand in front of your face. You cannot see the walls. You cannot see the floor or the ceiling. There is no up and no down except the pull of gravity through the soles of your suit. You stand in the dark, beneath the surface of Venus, inside a tunnel carved by fire millions of years before the first human being walked on Earth. And you think, if anything was ever here, it was here in this dark, in this silence, in this insulated, ancient, perfectly preserved darkness. If Venus ever had life, and it may have, and if that life needed somewhere to go when the surface became hostile, and it did, then this is where it would have come, down here. Away from the heat, away from the pressure, away from the acid sky, into the dark. You think, something could survive here, if the chemistry was right, if the water was right somewhere deep in the rock, if the energy sources were sufficient. You think, we do not know yet. We genuinely, completely do not know, but we are going to find out. You turn your light back on, the tunnel returns, ancient, vast, patient. You begin walking back toward the entrance, back toward the orange sky, back toward the heat and the pressure and the acid clouds that make Venus everything it is, back toward the surface of a world that has been hiding this place, this vast, dark, silent place for millions of years. And somewhere above you, 93 million miles away, on a small blue planet orbiting the same star, someone is listening to this, lying in the dark, wondering the same things you are wondering. The same question, the oldest question. Are we alone?